Welcome back, Allen High School pre-AP students. We're going to jump right into a discussion of the Bohr model, and we want to zero in on that, the best that the Bohr model gave us. Again, we want to move away from electrons orbiting a nucleus and move into instead the energy levels, because that's the beauty of what Bohr provided. It's what the atomic model is built upon. And in the Bohr model, we talk about an electron clouds or areas in space where electrons are most stable, and they're made up of energy levels. So it's kind of like the big picture is the energy level. Now, each energy level, it's like the rungs of a ladder. But here's the twist. They are not evenly spaced. Now, in a ladder and in stairs, if we don't have evenly spaced, we'll fall. Our bodies kind of get used to a cadence. But in this case, they're not evenly spaced. So the first one would be here, the second one might be there, and the third, and so forth. They get closer and closer together. We say that those energy levels converge. All right. Now, the amount of energy, and here we're talking about their potential energy. Potential energy possessed by an electron determines its position, and I'm going to add to that position relative to the nucleus. So the goal of an electron is to maximize the attraction to the protons, really, but to the nucleus, to the protons in the nucleus, but they want to minimize electron-electron repulsion. So they get as close to the nucleus as they can without sensing too much repulsion. All right. Levels farther from the nucleus represent a higher potential energy. It's actually less negative. So it's higher potential energy. So if we did a diagram, you're going to see one in a minute that's a little nicer. The nucleus is down here, and the further away the electron is, the higher the potential energy. Okay. Electrons like to hang out where they're most stable. And that stability, remember, is related to maximizing attractions, minimizing repulsions. This is called the ground state. I'm going to give you an analogy in just a minute on this. I think it'll help. It's the amount of energy they like to possess. You can kind of think of it as its home base. And all electrons have a ground state, but there's some flipping and flopping around. So I don't want you to think that an electron is fixed necessarily in a position, but we're going to draw models as if they are relatively in a fixed position in their stable state. So let's go on, and we're going to build up this model. Arg, if my little mouse doesn't keep jumping around. All right, here we go. Now, what we call these energy levels is we call them they're quantized. All right, so energy levels, when the only discrete levels. So here's, a staircase. A staircase has discrete steps. You can go up one staircase, you can go up two staircases, but you can't land halfway in between. A ramp, in theory, you could hit every single height above the ground if you just scooched slowly enough. This we would call a continuum. And these we would say they are quantized. So now, when an electron gains a quantum of energy, and we can do that by giving it heat or electricity, like the light bulbs that we have, fluorescent light bulbs, the electron will move up energy levels in a process called excitation. Now, in excitation, electrons absorb or take in energy. And electrons are going from a low energy level N, 1, 2, 3, 4, 1, N can be 1, 2, 3, 4, to a higher energy level N. And an excited state is very short-lived. I'm not sure what was in here, but I'm going to put short-lived in here. They can't stay excited for very long. And what they'll do is they'll fall back down to their ground state or fall as close as they can to the nucleus. And in the process, they will lose or emit energy. And it's always this time in the form of electromagnetic radiation. Here, it could be electromagnetic radiation, heat, or electricity, but when they move down or fall down, it's always released or emitted as electromagnetic radiation. And this process is called relaxation. Okay? And so if we saw that, the larger the fall, so if this was n equals 1, n equals 2, n equals 3, this, a larger the fall, it's a bigger distance than that. And so that's going to be a larger energy of light released. Okay? So this energy would be greater than the energy released there. Okay? And it's always released as electromagnetic radiation. So that's some background information, and that's in words. We need to see a picture, I think. I think pictures can speak to us so much more than words at times. And remember, we need to be able to draw representations that are graphs and pictures and words and symbols and math. We represent in a lot of different ways. So we're going to do this. We're going to talk about an energy level diagram. And do you notice the convergence here? The energy levels get closer together. This would be n equals 1, n equals 2, 3, 4, 5, and so forth. So when an electron absorbs energy, the process is called excitation. So let's say I'm at home in my ground state sitting in a rocking chair, and I get a phone call, and lo and behold, it is Denzel Washington. Let me tell you, I'm excited. I am going to move from my ground state into an excited state. I'm going to absorb energy just from the sound of that beautiful voice. And I'm going to be so very, very excited. Now, unfortunately, Denzel's going to very quickly realize he has the wrong number. And after I use up that energy, somehow I'm going to relax. This is your little old lady sitting in a rocking chair, probably with my cat in my lap. I'm going to relax. So in this case, the electron is going to emit the energy. I gave mine up by running around and calling my husband and my sisters and going, ooh, Denzel called me. But in the case of electrons, that energy is always going to be released as electromagnetic radiation. Okay? And that process is called relaxation. Okay? Now, this difference in energy between the two, and notice in this case we're going from high N to low N. This difference in energy, if I took the absolute value, that's going to be the energy of the photon that's emitted. Okay? And you've done the math on this. That means that the energy of the photon is hc over lambda. So the bigger the energy difference, so as you increase delta E, you're going to increase the energy of the photon released, and you're going to decrease the wavelength of light. You're going to make it shorter. All right? So we get different colors of light emitted. And that's what these diagrams are showing here. The visible is always going to n equals 2 is the visible. Others are in the ultraviolet and the infrared region. So this is the visible range. All right. And so you see these light coming off. This is a smaller energy difference So do you see that it's a longer wavelength of light? And this is a larger energy difference, so it's going to be a shorter wavelength of light. So this is blue and this is red. So blue is a shorter wavelength than red. Now, this is so exciting because it allows us to understand the structure of an atom. And that's what's really cool, because each atom has its own unique spectrum. All right, so let's take a look at these blanks. I'm going to fill them in quickly so this video won't be too long. Each possible energy fall corresponds to a different energy amount, and this corresponds to a different wavelength of light. Since different elements have different associations, so for n equals 1 for sodium is not equal to n equals 1 for lithium. They're different, and it all has to do with the fact that their nuclei are different. So this means that similar falls in energy level produces different wavelengths of light and has different colors. It's like a fingerprint. When we observe a color from an element, we're looking at the visible transitions when light is emitted, and they're all occurring at once. We can't split light with our eyeballs. It'd be really cool, but we can't. We have to use a prism or a spectroscope, and what we'll get is a spectrum. It's spectrum if it's singular, spectra, that's plural. Okay, and we're going to be looking at those more in class. So we'll talk about this bright line spectrum. Let me help you with that very, very quickly. Again, this video is a little long. I apologize for that. I like to make them shorter, but I don't want to have to renumber all my videos. Sorry about that. I'm being a little selfish here. So let's take a look. We've got a bright line spectrum. Here's lithium, here's calcium, and here's strontium, and then here's a mixture. What's in here? Well, these lines from calcium don't show up down here, so we don't have calcium. This line from lithium shows up. This line from lithium shows up, and so on. We can see those lines from lithium all showing up in our mixture. For strontium, we have the same thing. Strontium lines are all showing up in our mixture, and so forth. So we can see that lithium and strontium are in the mixture, but not calcium. So we can identify elements found in a mixture as well as identify the elements themselves, because an atomic emission spectrum is like a fingerprint. So you got that full name again. Atomic emission spectroscopy. Okay, so until I see you in class, this is your best or beloved chemistry teacher signing off.